Okay, so this is chapter 11, section 5, exploring solids. It's going to be a pretty quick section. It's very definition heavy, not a lot of mathematics really involved. They start off by talking about a polyhedron, and a polyhedron is a solid, a three-dimensional figure. Solid is a three-dimensional figure that the book says is bounded by polygons called faces, enclosed single region of space. Edges of the polyhedron is the line segment formed by the intersection of two faces, and the vertex of the polyhedron is the point where three or more edges meet. Plural polyhedron is a polyhedra or polyhedrons. Okay, so we have a polyhedra. This one right here. It has basically a polyhedron is a three-dimensional figure whose sides are polygons, shapes, squares, rectangles, triangles, hexagons, etc., etc., etc. If you look at this particular polyhedron, the highlighted here as a face, and notice that it has a shape of basically like a square. It has other faces too. There's a face to the left, which is in the shape of a rectangle, to the right, which is in the shape of a rectangle, to the back, which is a trapezoid, to the front, which is a trapezoid, and if you look at the bottom, the shape is a rectangle. So all of those are polygons, so we can say that this is a polyhedra. The edge of a polyhedra is where two faces intersect. So if we look up here at the top, we have this face going this way. We have the trapezoid, which is going that way, and they both intersect right here in the front. And this intersection is called the edge. And if this was labeled, it would be labeled as a line segment. We also have the vertex, where three faces meet, and it forms at the corners, so at the points. So here's the front trapezoid, here's the side rectangle, and here's the bottom rectangle, and they all intersect right here at the front. So we have a vertex here, a vertex in the back, a vertex in the back down here, and four up top, where three or more faces meet. Here's examples of polyhedrons. We have a prism here. Again, all of its faces are polygons, has corners and edges. Pyramid, again, all its faces are polygons. We have a rectangle or square in the bottom, and then on the sides they're all triangles. Then we have non-polyhedrons. And non-polyhedrons are three-dimensional shapes where their faces are round. There's no edges, there's no sharp corners. So we have a cylinder where both of its bases are circles. We have a sphere, which is round and circular, no sharp edges and corners. We have a cone, which has a vertex, but doesn't have edges as we know it. So they're called a non-polyhedron. When we have a prism, we have a pair of prisms have two bases. Prisms have two bases, and their bases are always going to be identical. They're going to be congruent. They're going to be the same shape, and they're always going to be parallel. So if you look at this, we have a pentagon on the bottom. We have a pentagon on the top. They're opposites. They're parallel. They're never going to intersect, and they're always going to be identical. So prisms always have two bases. Pyramids always have one base, and the base is always going to be some shape opposite of the vertex, where all the faces, the lateral faces of the pyramid intersect at the top. Pyramids, one base. Prisms, two bases. So they want you to tell if one is a polyhedron or not. A, yes, because it's has it's a rectangular prism, so faces are all polygons. B, yes, it's a it's a hexagonal prism, pyramid, and it's definitely a polyhedron. C, no, it's a cone, round base, not a polyhedra. Which reminds me, when we label these things, like it's a prism, right? And it's called a pentagonal prism. And it's called a pentagonal prism because the base is a pentagon. So whatever shape the base is the name that we give either the pyramid or the prism. If the shape is a rectangle, we call it a rectangular prism. If the base is a triangle, we call it a triangular prism. If the base is an octagon, we call it an octagonal prism. Same thing for pyramids. If the base is a triangle, which is in this case here, then it's a triangular prism. If the base is a square, we would call that a square pyramid. If the base is a nanogon, we call it a nanogonal pyramid. Whatever the base is the name that we give that particular prism or pyramid. That should be in your book too. So down here, they want us to find the solid and tell whether if it's polyhedron or not, and then faces, vertices, and edges. So, number one is a square pyramid, and all the sides are the same on the base, so that tells me it's a square. It's a polyhedron. Number two, it has two rounded bases. So this particular shape is not a polyhedron. And then number three, it's a triangular prism because the two bases are triangles, and it is a polyhedron. So when I look at the polyhedron for number one, if I was looking at the edges, I would just count the sides where two faces meet. So I have one here, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 edges. Vertices are the points. I don't spell vertices. I probably spelled it wrong. So I have 1 up top, 2, 3, 4, 5. So I have 5 vertices. And then faces, I have 1 triangle in the back, 1 in the front, 1 on the side, 1 to the other side. So 1, 2, 3, 4, and then 1 on the bottom, which is 5. So faces, I also have 5. So that's for number one. For number two, the triangular prism, I have edges. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I count 9 edges. Of course, you can always double check if you got to count these by hand. 1, 2, 3, 4, 5, 6, 7, 8. 9 edges. Vertices, I got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. I count 6. And then faces, I got 1, 2, 3, 4, 5. 5 faces. Don't like those numbers. But yeah, you can count them. We didn't do number 2 because number 2 is in a polyhedron, so you can't get really a lot of vertices. There's an easier way to find the faces, edges, and vertices, and that's called Euler's formula. And Euler's formula is a face plus the vertices is equal to the edges plus 2. Face plus the vertices is equal to the edges plus 2. And you could use that, which is a lot easier than counting and making boo-boos. Alright, so really want to go through the example. Euler's formula is pretty straightforward. Polyhedron can be a regular polyhedron, meaning that all the faces are the same, congruent. and they're regular. We can also have a convex polyhedron, which says that any 2 points of the surface uh, can be connected by a line segment. So basically saying there's no indentation into our particular polyhedron. So if you look at the regular convex to the left, uh, everything is connected by a line segment. There's no indentation. Here we have a non-regular concave. Concave meaning that there is an indentation. You see that there's an indentation over here. So therefore we would call that a concave. And since not all the sides are the same, it would be concave and non-regular. So concave, indentation, you cannot connect each side with a line segment. Convex, each side can be connected with a line segment. Platonic solids are 5 specific polyhedra associated with the Greek philosopher Plato, and pseudo-mathematician and geometry guy. We have a regular triangular polyhedron, which is a tetrahedron rather, which is a triangular pyramid-esque type thing. We have a cube, and we have a regular octahedron where it's basically 2 square pyramids connected at the base. We have a regular dodecahedron, which has 12 faces, and we have a regular icosahedron. A regular icosahedron is kind of interesting for those who like soccer. If you cut all the vertices where they meet, it's called a truncated icosahedron, which is the shape of the soccer ball, for those who care. All right. So you can use Euler's formula. If you want, they'll give you certain information, and you can use the face plus the vertices equals the edges plus 2. Now, it's a pretty straightforward equation, so I don't really feel the need to go over it. Cross-section. A cross-section is when a plane intersects a particular solid and it forms a 2-dimensional shape. So here we have an example of a plane intersecting with the pyramid, and their intersection point forms the cross-section. And if you notice, the cross-section is a triangle. So you get a two-dimensional shape out of using a plane intersection with a solid to form that cross-section. Cross-sections are always 2-dimensional shapes. Down here, we have a horizontal plane intersecting a cube, which forms a square. We have a diagonal plane intersecting a cube, which forms a rectangle. And then we have an sort of oblong plane intersecting a cube forming a, notice you have different size bases and pillar sides, it forms a trapezoid. So for these guys, this plane for number 5 intersecting the cube is forming a triangle. This plane is intersecting the cone, and it forms a circle from that intersection. And then this plane is intersecting a hexagonal prism, and it's forming a hexagon. And that's it, guys. That is section 11.5, Introduction into Solids. Told you it wasn't a lot of math. You guys have a great rest of your day.